Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. We are in the second module. The title of the second module is Working Principles of Shearing Viscometers. In this one, first we see capillary viscometers. Before going into the details of the shearing viscometers, we have a recapitulation of what we have studied in the previous module. In the previous modules, we have seen different characteristics of the Newtonian fluid behavior, and then similarly different characteristics of the non-Newtonian fluid behaviors and the types of non-Newtonian fluids, time dependent, time independent and viscoelastic fluids, etc. we have seen, and then different mathematical models available for the non-Newtonian fluids we have seen. Also we have seen some example problems under each category of non-Newtonian fluids. So, having seen the basic concepts, basic classification of non-Newtonian fluids, it comes to the mind, how do we know whether a given material is Newtonian or non-Newtonian? If it is non-Newtonian, what type of non-Newtonian fluid it is? How to measure the rheology of these non-Newtonian fluids? For that purpose, we have the viscometers or rheometers. Now, these viscometers will provide us some kind of information about shear rate versus shear stress, or shear rate versus normal stresses, or both. Before going to the details of the capillary viscometers, we have some introduction about viscometers. So, introduction under this part gives us some information about the how difficult is rheology, and then what are the parameters are usually affecting the rheological measurements, etc. So, we already understand that non-Newtonian fluid behavior is a very complex complicated behavior, and then same fluid may give a different types of non-Newtonian behavior if the range of shear rate is changing. So, some materials also shear dependent, time dependent, or both, and then some materials are also viscoelastic in nature. We have seen mathematically how complicated are those models, etc. Now, so what we understand, obviously the rheology of this non-Newtonian fluid is not going to be straightforward, and even for some cases such as concentrated suspensions, etc., this may become even more complicated due to nonlinear, dispersive, dissipative and thixotropic mechanical properties. So, it is useful if the rheology measuring system provide constant or nearly constant shear rate, which can be achieved by narrow gap shearing geometries. So, what happens, let us we take a kind of example of flow through pipe or a capillary. Let us say if this is your geometry and if this is the center of the geometry, usually the velocity is maximum at the center and then it is 0 at the wall because of the no slip. If it is a Newtonian fluid, that we know that this behavior is something like this. Now, the velocity is changing from 0 velocity to maximum velocity as we move from the wall of the tube to the center of the tube. So, obviously velocity gradient is also changing. So, then that means the shear rate is also changing. If the shear rate is changing across the cross section of the geometry shown here, so then which value of the shear rate should be taken? So, it is primarily important that whatever the geometry system that you take for measuring the rheology of a fluid, it should provide a kind of a constant or almost constant shear rate for a given fluid. How can we achieve this constant shear rate or almost constant shear rate? This is possible if you can have a very narrow gap shearing geometries, such as like coaxial, cylindrical geometry, cone and plate geometry. If it is capillary geometry, very narrow diameter capillaries, etc. So, under that condition, since the gap is very narrow, so then shear rate change in the velocity from wall to the center will definitely be there, but that change would be small. Similarly, change in the velocity gradient would be there, but that difference from center to the wall or wall to the center would be very small or negligible. So, that will give us a kind of a constant shear rate or almost constant shear rate. However, such narrow gap measuring geometries are often of limited utility, especially for non-Newtonian fluids, because non-Newtonian fluids are in generally multiphase products such as suspensions, foams and emulsions, etc. So, if the gap is very narrow, whatever the particles there in the suspension of non-Newtonian suspension, the particle or droplets or bubbles may break up, and then obviously the property of the material may change under such narrow gaps, or otherwise in other way, if the material that is subjected under these narrow gaps, if it is having high viscosity, then also there is possibility of the viscous dissipation, and because of the viscous dissipation the fluid temperature may change because of that viscous dissipation, and then accordingly the rheology may also change. That is, in other way, constant temperature condition may not be maintained. So, however, measuring geometries do not approximate to constant shear rate. So, various measurement strategies have been devised to overcome such kind of limitations. So, but we will not go into details of those limitations and all that in general, but we go one by one. First we take now capillary viscometer. Capillary viscometer is most commonly used because of its simplicity, low cost and accuracy, provided the diameter of the capillary is very small and then length of the capillary is very large, or L by D ratio of the capillary is sufficiently large enough, that is more than 100 or so. In order to devise this equipment, you need to have a barrel in which you can take the fluid of which rheology you wanted to measure, and then to this barrel you can connect a capillary tube of a small diameter and large length, sufficiently large length in a right, and then you can apply certain pressure to get a fluid out of the capillary. So, then you can measure the volumetric flow rate versus delta P information. From that volumetric flow rate versus the pressure gradient information, you can obtain the shear stress and then shear rate information as we are going to discuss in this lecture, and then you can find the rheology of that particular fluid. However, capillary type of viscometers are often restricted to time independent non-Newtonian fluids, where you can get only shear stress versus shear rate information only. Because of their similarity to many process flows involving pipes, it is widely used in process engineering applications and are often converted or adapted to produce slit or annular flows. So, we have in general in applications several cases where flow through pipes takes place. So, these capillary viscometers can also be used as a kind of inbuilt inline viscometers as well. Now, in order to develop the working principles of the capillary viscometer, what we do, we consider a circular capillary of very small diameter but very large length, and then within this capillary consider only a limited in between range where the flow is fully developed. What does mean by flow is fully developed? That is, the in the flow direction the flow variables do not change. That is, let us say here in this case the flow is taking place in the z direction. So, then dou by dou z of any flow variables is 0 for given this system. That is what mean by fully developed flow. Or otherwise, let us take the case of parabolic profile for a Newtonian fluid. If the flow is fully developed at any length in the z, at any location in the flow direction, the profile if you plot, it will always be parabolic like this, it will not change. That is what it mean by parabolic profile. That is what it mean by fully developed flow. That is, here if the only z component of velocity is existing, then dou Vz by dou z would be 0. So, in this case what we take, the flow of the fluid is due to the pressure difference that is imposed across the two ends of the pipe. Now, what we do, we need to do momentum balance for this system, and then try to develop the respective equations which we need in order to ascertain the rheology of the fluid. So, we make an assumption that there is only a laminar steady incompressible flow, under fully developed flow conditions. There is no angular velocity, there is only z component of velocity is existing, that is changing only in the radial direction, and that is possible and then true assumptions as long as the diameter of the capillary is small enough, very small enough. So, here in this capillary we take a region, fully developed region, for which the schematic is shown here. So, within this fully developed region, take a volume element or fluid element of volume A, B, C, D. Here the pressure at the inlet of the fluid element is P, whereas the pressure at the outlet of the fluid element is P plus delta P. The radius of this element, volume element or fluid element is R. The length of the fluid element or the volume element consider is L. The shear stress acting on this fluid element is tau R z as shown here. Why tau R z only? Because here the diameter of the capillary is very small and the flow is laminar steady state. So, only V z velocity is existing and then that V z velocity is varying in only R direction. So, only one shear stress component will be there, that is tau R z, rest all stress component would be 0. Now, for this volume element, since we have considered there is no angular velocity, we can do a linear momentum balance for that fluid element that A, B, C, D that we have considered. So, how we can write the balance? So, we can write P into pi r square minus P plus delta P pi r square is equals to tau r z multiplied by 2 pi r l. So, from this balance equation, what we can get, if you do the simplification, we get tau r z is equals to minus delta P by L r by 2. So, what we understand here, till now we have not imposed any kind of assumptions like whether it is a laminar flow or turbulent flow, or till now we have not made any assumptions on the nature of the flow or the nature of the fluid. So, this expression whatever given here tau r z, that is valid for all fluids, all irrespective of the nature of the fluid, we can use this expression. Also, we can see that tau r z is proportional to the pressure gradient, and then we can see that this tau r z is linearly varying with the distance r. So, that is it is 0 at the center of the capillary, and then it is maximum at the wall of the capillary, that is at small r is equals to capital R. So, then this maximum shear stress is also known as the wall shear stress, because we are evaluating it at the wall of the capillary tube. So, that can be written as tau w is equals to minus delta P by L capital R by 2. So, in the rheology, in order to know the rheology of the considered fluid, we know the shear stress here. Tau w, that is wall shear stress, we can know once the delta P or pressure gradient, applied pressure gradient is known, that we can know. So, other information that you need to know is the shear rate. If you know the shear rate, then your information is complete to get the rheology of the time independent non-Newtonian fluids. Then using the tau w versus gamma dot w, you can get the you can know the rheology of that particular fluid. So, about the next part, second part, that is getting the shear rate information or expression for the shear rate. What we do? We do take two fluid elements of radius r and then radius r plus dr, or consider a fluid element of thickness delta r or dr. So, now if you wanted to know volumetric flow rate through the annulus formed by these two fluid elements of size r and r plus dr, you can get it as dq is equals to 2 pi r Vz dr, where Vz is function of r. Now, if you integrate this dq is equals to 2 pi r Vz dr over the cross section of the pipe, you can get the volumetric flow rate, that is total volumetric flow rate of the fluid flowing through the capillary. So, let us do that one. So, now in order to get the total volumetric flow rate, let us integrate this expression. So, integral of dq is equals to q is equals to integral 0 to r 2 pi r Vz dr. So, now r and Vz both are function of r. So, we have to apply this integral uv kind of formula, integration formula to integrate this one. So, now let us take 2 pi common. So, now first integration of r is r square by 2, then Vz as it is, apply the limits 0 to r minus integration of integration of r is again r square by 2, and then differentiation of Vz is dVz by dr, but I have written minus dVz by dr, and then here this one I made it as a plus. So, now you apply the boundary conditions or apply the limits 0 and r in the first term in the right hand side of the equations. So, then we get 2 pi r square by 2 r 2 pi r square by 2 Vz at r is equals to r minus 0 square by 2 Vz at r is equals to 0. We know that at r is equals to capital R, that is at the wall of the tube, circular tube, the velocity is 0 because of the no slip boundary condition. So, now altogether this particular term become 0, then q is equals to pi integral 0 to r square minus dvz by dr. Now, from this equation what we understand, that there is some kind of relation that between minus dvz by dr, which is nothing but your shear rate, and r gamma dot. So, gamma dot versus volumetric flow rate, we have some kind of information, but still there is an integral. So, it is not completely in the usable format. So, we do further simplifications. However, now here in order to go next step, we have to make necessary assumptions regarding the nature of the flow and the characteristics of the non-Newtonian fluids. So, now for laminar flow of time independent fluids, okay, so that we take the laminar flow and then we take the time independent fluids as of now. So, then shear rate versus shear stress information can be related or put as minus dvz by dr is equals to f of tau rz. F is a function, unknown function, which describes the rheology of the fluid, but however, here we do not know what is the rheology of the fluid. So, then we take it as a unknown function. Otherwise, let us say if it is a power law fluid, that we know that tau rz, for power law fluids we have already seen that this f of tau rz is equals to minus dvz by dr. This we know as tau rz is equals to m into minus dvz by dr whole power n. This is the relation between shear stress versus shear rate for a known fluid, for a known power law fluid, but as of now we do not know what is that fluid. We are measuring, we are going to evaluate what type of fluid it is. So, for that in order to know what type of fluid it is, we are developing corresponding equation. So, let take it as minus dvz by dr is equals to f of tau rz. Now, but we have already seen that tau rz is equals to minus delta p by L r by 2, and then tau wall is equals to minus delta p by L capital R by 2. From these two relations we can get that tau rz by tau w is equals to small r by capital R. From here we get dr is equals to r by tau w d tau rz. Now, we have already derived in our equation previous slide that q is equals to pi into integral 0 to r square minus dvz by dr. So, in this equation what we do, we substitute what is r, what is dvz by dr, what is dr. So, then we get here. So, r is nothing but we can get r is capital R tau rz by tau w. So, r square is r square tau rz square by tau w square minus dvz by dr is nothing but f of tau rz. Then dr is nothing but from equation 7 r by tau w d tau rz. Now, if you rearrange this equation, or otherwise if you take pi r cube by tau w cube separate outside of the integration, so you get q is equals to pi r cube tau divided by tau w cube integral tau rz square f of tau rz d tau rz from 0 to tau w. So, further this equation can be simplified. What we do before simplifying, we make a kind of analysis. We understand from this equation that in the left hand side everything is function of tau w, or you will get the values in terms of tau w etc. In the right hand side we have integration in tau rz f of tau rz d tau rz kind of thing, but after integration whatever may be the function, after integration when you substitute this limits 0 and tau w, you will get the final answer in terms of tau w only. So, what does it indicate? It indicates that if you know tau w information, that is sufficient enough. So, corresponding gamma dot w information, that is sufficient enough in order to ascertain the rheology of the fluid. So, now what we do, this equation we differentiate both the sides with respect to tau w. So, then we get this equation. Now, keep the left hand side of this equation as it is. In the right hand side equation, this is of the form where we can apply Leibniz rule. According to Leibniz rule, we have d by ds prime integral s square f of s ds limiting 0 to s prime, we get s prime square f of s prime. So, now here in this above equation, what we do, we can see that from the above equation comparing with the Leibniz rule, s is nothing but tau r z and s prime is nothing but tau w. So, this equation left hand side will remain as it is. In the right hand side, in place of this d by d tau w integral tau r z square f r z d tau r z, we can write tau w square, that is s prime square, and then f of tau w, that is nothing but f of s prime. So, we have further simplified this equation in a more usable form. So, now this equation whatever we have got here after applying the Leibniz rule, d by d tau w of cube tau w cube by pi r cube is equals to tau w square f of tau w. Still we do not know what is f of tau w, but however we try to simplify it now. So, now in the left hand side, q is not independent of tau w, because q is related to the delta p and tau w is according to delta p, tau w will also change. So, when you differentiate, you have to differentiate both q and tau w. So, we get q by pi r cube as it is, keep constant first time, and then differentiation of tau w cube is 3 tau w square, plus now you keep tau w cube as it is, and differentiation of q by pi r cube we cannot differentiate because what is the q. So, keep that as it is in the differential form. In the right hand side, nothing, no changes are required. Now, this equation you rearrange such that f of tau w remains one side and then all other terms are in the other side. So, then we get f of tau w is equals to 3q by pi r cube plus tau w d by d tau w q by pi r cube. So, in this equation number 11, what we will do, in the right hand side we make use of factor 4 for both the terms, that is both first and second terms we divide and multiply by 4, and then we apply identity d ln x is equals to dx by x form. So, then we can write that f of tau w, which is nothing but minus dvz by dr at r is equals to capital R. So, first term now multiplying by 4, dividing by 4. So, then we have 4 cube by pi r cube multiplied by 3 by 4. Second term we are dividing and multiplying by 4. Equation number 11, second term in the RHS side, that can be written as d ln 4 cube by pi r cube divided by d ln tau w multiplied by q pi r cube. So, when you simplify this equation, you will get the second term in the RHS of equation number 11. So, it is the same equation. So, now from these two terms in the RHS of this equation, what we do? We take common 4 cube by pi r cube. So, then we get 3 by 4 plus 1 by 4 d ln 4 cube by pi r cube divided by d ln tau w. So, now we have a equation for shear rate also. Shear rate, that is wall shear rate, that is minus dvz by dr at r is equals to capital R from this equation. But if the same equation if you wanted to write in terms of the average velocity and then diameter of the pipe, average velocity is q by pi r square and then diameter of this capillary pipe or capillary tube is d. So, apply this one and simplify this equation number 12. So, then we get an expression for the wall shear rate, that is gamma dot w r minus dvz by dr at small r is equals to capital R is equals to 8 v by d multiplied by 3 by 4 plus 1 by 4 d ln 8 v by d divided by d ln tau w. However, we already know that 8 v by d is a shear rate, is the true shear rate for a Newtonian fluid flowing through a capillary under laminar flow conditions, under laminar and fully developed flow conditions. So, 8 v by d is shear rate for a Newtonian fluid flowing through a capillary under fully developed laminar flow conditions. So, whatever the additional correction factor, additional term is there here, that indicates the correction factor due to the non-Newtonian behavior of the fluid. Let us say you do the experiment through the capillary flow through capillary, obtain q versus delta p information, and then if this correction comes out to be close to 1 or is equals to 1, then you can say that fluid is a Newtonian fluid, or if it is not equals to 1, then that fluid is obeying some kind of non-Newtonian fluid behavior. Accordingly, you can get the correction for corrected shear rate, which will give you the true picture of the rheology of the fluid. So, how do we know that 8 V by D is a true shear rate for a Newtonian fluid? Because we know for a laminar fully developed steady Newtonian fluid in pipe, according to Huygens-Poiseuille equation, that is nothing but minus delta P by L is equals to 32 mu V by D square. So, let us rearrange this equation as V is equals to minus delta P by L R square by 8 mu. Further, we can write it as minus delta P by L R by 2 multiplied by R by 4 mu. Now, you keep minus delta P by L R by 2 one side and then remaining terms other side, that is 4 mu V by R, that is you can write 8 V by D mu. So, tau this left hand side minus delta P by L capital R by 2 whatever is there, that is nothing but the wall shear stress for a Newtonian fluid, and then mu is nothing but viscosity of that Newtonian fluid. So, this 8 V by D whatever is there, that should be your wall shear rate for that Newtonian fluid. So, from that previous equation 8 V by D is like apparent or nominal shear rate of that fluid, and then whatever the correcting factor in the parenthesis is there, that gives a correction because of the non-Newtonian behavior of the fluid. Now, whatever the equation 13 that we have minus dVz by dr at r is equals to r is equals to 8 V by D multiplied by 3 by 4 plus 1 by 4 d ln 8 V by D divided by d ln tau w. Now, this information, if you plot on a log plot, that is tau w versus 8 V by D, then you will get a then you may get a straight line of slope n prime, which is given as n prime is equals to d ln tau w by d ln 8 V by D. This value of n prime will indicate the nature of the fluid, whether it is Newtonian or non-Newtonian. If it is a Newtonian fluid, then we will get n prime is equals to 1. If it is a shear thinning fluid, we will get this n prime values less than 1. If it is a shear thickening fluid, we get value of this n prime greater than 1. So, now that equation this equation 13, if we rearrange and write it as like gamma dot w is equals to 8 V by D multiplied by 3n plus 1 or 3n prime plus 1 by 4n prime, this will give you the true shear rate for that particular fluid, where slope n prime may vary with nominal shear rate. Nominal shear rate 8 V by D is the nominal shear rate or apparent shear rate, which so this n prime value may vary with this nominal shear rate value if the fluid is a non-Newtonian fluid. So, now we have the information about wall shear stress and then wall shear rate. Wall shear stress information, that tau w we have already got it as minus delta P by L capital R by 2. So, and then wall shear rate gamma dot w we got it as 8 V by D multiplied by 3n prime plus 1 by 4n prime. So, now for a case flow through a capillary, if you have a Q versus minus delta P information, from that information what you can do, you can get tau w and gamma dot w information, right. Q may be again related to the V, because V is equals to Q by pi r square. So, if V is known, Q is known, that means V is known. So, for a capillary of known length and diameter, if the Q versus delta P information is known, from this Q versus delta P information you can get the tau w. Using the delta P minus delta P by L information, you can get tau w. Using the corresponding Q or V, you can get the gamma dot w, true shear rate for that fluid you can get by using this equation number 16. So, this is how using a capillary viscometer you can get the information about the rheology of time independent non-Newtonian fluids. Only thing that you need a simple barrel which is filled with the fluid whose non-Newtonian behavior you wanted to measure, and to that barrel a capillary should be connected. Capillary of small diameter and large length, sufficiently large enough length should be connected, and then apply certain delta P, obtain the flow rate. So, this Q versus delta P information you can get from that capillary viscometer, and then using that Q versus delta P information you can apply here in these equations for tau W and gamma dot W. Then you plot tau W versus gamma dot W. If it is passing through origin and straight line, then that fluid is a Newtonian fluid. If it passes through the origin, but obeys non-linear behavior. So, depending on the non-linearity, it can be shear thinning or shear thickening fluid that you can ascertain. Similarly, for the viscoplastic fluids also you can do the same thing, similar experiment. So, these viscometers are actually in general operated in two modes. One is the constant flow rate mode, another one is the constant pressure device. So, in general constant flow rate device or constant flow rate mode is applied for the high viscous polymer melts, resins and thick suspens, etc. Constant pressure devices are used for low to medium viscosity fluids. However, irrespective of the type of the fluid, it has been found that the constant flow rate devices are much more appropriate and reliable compared to the constant pressure devices. In general, pipe viscometers having straight cross sections of pipe are used in industry settings for quick measurements. Wherever the pipe is horizontal pipe is there, so you can flow is taking place, you can measure the flow rate for a given delta P, and then quickly you can ascertain the rheology of that fluid from that Q versus delta P information applying the equations we have just derived. So, basically whether it is constant flow rate device or constant pressure device, what you get you get the information Q versus delta P. That information is sufficient to determine the rheology of a given fluid. Now, we take an example problem and try to obtain the rheological characteristics of that particular fluid for which the data is given. So, a high pressure polyethylene melt at 190 degrees centigrade has been applied or allowed to flow through capillary viscometer at different delta P values. So, whatever the Q versus delta P information or Q versus pressure drop information is there, that has been converted into 8 V by D, that is nominal or apparent shear rate, and tau W, that is wall shear stress information, and they are given in second inverse and kilopascal respectively. So, this is the information. This information is coming from the Q, this information is coming from minus delta P by L. Whatever Q versus minus delta P by L information is there, that has been converted into the 8 V by D and then tau W respectively, and then that information has been given in a tabular column shown here. So, tau W wall shear stress is the true shear stress. So, we do not need to do any corrections, as we have already seen in the working principles or equations that we have just derived, but we know this 8 V by D is nominal or apparent shear rate, it is not the true shear rate of the material. So, what we need to do? We need to obtain that correction 3n prime plus 1 by 4n prime, and then see if it is a Newtonian fluid, then this 8 V by D is a true shear rate, and then that correction 3n prime plus 1 by 4n prime will come close to 1. So, now what we do? We make use of these two equations that is already derived just now. Gamma dot W is equals to 3n prime plus 1 by 4n prime 8 V by D, and then tau W is equals to minus delta P by L R by 2. So, this is already given, we do not need to do anything. So, only thing that you need to find out n prime value, because 8 V by D is also given for a wall shear rate information, that is apparent wall shear rate is given. So, now how to do? What we need to do? You need to plot this information in a log plot tau w versus 8V by d or log tau w versus 8V by d. So, then you may have a curve something like this. So, now at each point you have to draw a tangent at each point, right. So, the slope of the tangent is nothing but n prime. Then once you get the n prime, you obtain the corresponding new gamma dot w values or true shear rate information. If they are if the if the slope n prime is coming close to 1, then or equals to 1, so then correction is equals to 1. So, whatever the information 8V by d is given, that is true shear rate only, you do not need to do any correction. But now let us see in this case what is the value of n prime for each value of tau w. So, when you do, as I shown before, on a log graph, you plot tau w versus 8V by d or log tau w versus log 8V by d, and then get the n prime value at each point. So, then we can see now at each value of tau w, the corresponding n prime value is changing, and then it is changing drastically 0.5 to 0.3 as tau w is changing from 22 to 164. So, these n prime values are changing drastically for each tau w value. It is changing from 0.5 to 0.31 as tau w is changing from 22.4 to 164. Now, corresponding gamma dot w, that is nothing but 8V by d multiplied by 3n prime plus 1 by 4n prime. This correction, if you see, this is also changing the true this is the true shear rate. The given apparent shear rate, you can see apparent shear rate first point is 10, whereas true one is 12.5. The when the apparent shear rate is 200, the true shear rate is 275. When the apparent shear rate is 2000, the true shear rate is 3113, that is a very large value. And further we can see that n prime value is also decreasing as tau w increasing. So, this and then all of these n prime values show obtained are less than 1. This indicates that a fluid is a shear thinning fluid, and then given 8V by d information is not the true shear rate, but the apparent or nominal shear rate only. The corrected or the true shear rate for this material is given here. So, this is how you can know the rheological behavior of time independent non-Newtonian fluids using the capillary viscometers. Details of the capillary viscometer discussed in this lecture are taken from the reference book Chabra and Richardson. That is a very good book for non-Newtonian rheology. Thank you.